Yeah, okay. So, we're going to learn now how to make a histogram of this data. And we're going to go through it kind of slowly here. It'll be nice, again, having the repository on the video so you can go back and look at it again if you need to. So we're going to turn this data, this single list of raw data, into a graph to make it more visual. So here's the steps to get a histogram on an 8384. First thing you want to do is press the second function button, which on mine is blue. Some of you may have a yellow one because it's a T83, totally fine. Lucas?
So you know when you asked Monday if anybody had an 89?
Yes.
And no one said
Michael
yes?
does.
Yeah.
We're on it. We're on it.
Oh,
and I'm going to send him. Well, he wasn't here.
Check it out.
He wasn't here. And we're going to get him the actual guidebook for it, so we're solid. Thank you, Lucas. Thank you. So you press second. Now press Y equals. This is your stat plot screen. Right above Y. Usually Y equals, you would graph stuff in Math 95, Math 111. Here you're going to be graphing stat plots, histograms, scatter plots, box and whisker plots, all kinds of good stuff. You have the option to turn on up to 3 at one time. We'll probably do no more than 2 at a time, which is good. We're going to start with 1 at a time right now. And let's start with plot 1. So either type 1 or enter, either one will do. And this takes you to your setup screen. This is your setup screen, okay? So, first of all, turn it on. Now you get to graph something. But you got to make sure you set it up properly first. If you tried to graph this right now, you'd get an error. And you'll see why later. We don't want this type of graph. This is called a scatter plot. We don't want that right now. We don't want a polygon. We want that guy right there as a histogram. So arrow down until you're in that line, then arrow over until you're on top of the histogram, and then press enter. And then press enter. So far we've turned the plot on, yay, and we've selected histogram, good to go. That doesn't mean it's going to be that shape, it just means that's the default shape they put in the graph. Fair enough? All right. X-list. This next choice down here, it says X-list. That's where your data is. Does your guy's X-list say L1? If it doesn't, everybody do this anyway. Press second 1. Because if it didn't say L1, you'd have to make it say L1. So second 1 gets that to you. What does your frequency list say, friends? Does anybody just say the number 1? Good. They should say that. Because we have raw data. Frequency, what does frequency mean again? What is frequency? Say that again. Be nice and loud. How often it happens. How many times that data point happens. If you have raw data, each data point happens one time. One time. Mine says L2. Does anybody else say L2 or anything else besides 1? Just to give you a heads up, I have to change that to 1 on mine. If I try to type 1 right now, I get a letter Y. That's because if you notice, as soon as you jump into X list and Y list, there's an alpha code on the little A code. It's a bug. TI never took off. You have to turn alpha mode off by pressing the alpha button, and then you can type the number. So everybody practice that right now. Put your blinker on frequency where it's blinking on 1, and I want you to retype 1. So you can't just hit 1. You have to hit alpha first and then 1. Make sense? Yes. I only say this because throughout the course, on average it falls as the course goes on. I keep saying, how do I get the Y off? That's how. Alpha and then 1. So whenever you see that little A button blinking, just realize, turn that off before you. I don't know why they put that in there, but they did. Coolish? Yes? Excellent, excellent. Okay, we're set up, friends. We're ready to go. So once you've got your graph on, your type histogram, your X list of L1, your frequency 1. As a matter of habit, depending on, some of you have 84s, some have 83s, and there is a bug TI never fixed built in. Before you do this next step, you probably want to put your cursor back up on. Don't press anything, just put it up there. Get it away from the alpha button, basically. I don't want that alpha thing blinking. And now the easiest way to get a graph is to press the zoom button, which is right in the middle of the top row, zoom, and then the number 9, which is called zoom stat. And hopefully we all get this graph right here. Hopefully we all get this graph, which is our histogram.
I'm sorry, Mrs. Steph. So after we get everything done, we just put graph?
No, zoom 9 for now, Raphael. Zoom 9, what zoom 9 does, friends, there are a series of zooms in the zoom menu that make graphing allegedly easier. What zoom 9 does, zoom 9 is actually called zoom stat, zoom stat. What it does is it picks a window based on the data that you input. And I'm also going to turn off this graph from Y1, which got in the way. Yeah, if you have anything in Y1, turn that off too. I forgot about that. So hopefully we all have this graph. Fair enough? And what's so great is if you need a backup or to review, you can just go back to the video and pull it up there. It's fantastic. Now, we all have the exact same graph. The default that TI uses is it gives you 7 spaces for bars. So you got 1, 2, 3, 4, 5, 6 bars and a space for a 7th. I like to finagle with that sometimes because those bars are usually not a sensible width wide. Like in your homework, a couple homeworks ago, you had to set up a histogram where you were like 18 to 24, 24 to whatever it was, 36 or something. I forget exactly how wide things were, but they were all kind of a uniform, sensible width. If you press the window button right now, the window button, which is right next to zoom, this is how wide those bars are. They're 13 1/6 pounds wide. That's kind of a dumb number. I mean, I say dumb because it's too hard for us to add that kind of thing in our head. I like to use nice normal numbers like 10 there. If you change that to 10, and then you press graph again,
Always piss me off at 95.
then you see you now have more bars. That's because the bars are now narrower, which means you have more of them across. So this number down here, what's the smallest number you see here on your screen?
-50.
And you can tell that also from the window screen, can't you? If you press that window button, X min is at -58. I want to make it -60, if it's okay with you guys. I'm playing with some Math 95 skills here, just trying to get used to the windows. Did you guys use TIs a lot in Math 95?
Yeah.
Yeah. And hopefully you spend a lot of time finagling windows, because I like, for histograms especially, I love getting there and kind of dorking with them to make the numbers easier to tolerate and use. And I want to use this histogram a lot today. This upper number of 34, what was our highest weight gain?
Our highest weight gain?
Oh, I can look back at my list, can't I?
No,
58.
21.
Oh, weight loss.
21? Right, 21?
Yeah.
So somebody gained 21 pounds on this program?
Yeah.
So there's 21 right there. So what I'm going to do is I'm going to make X max not 34, but I'm going to make it 30, which is the next whole number above 21. So all I'm doing is I'm trying to make the divisions on the horizontal axis more logical. So now when you press graph, there's your histogram. -60, -50, -40, -30, -20, -10, 0, 10, 20, 30. Fair enough? Now, you can get ridiculous with this. You can. For example, you can break up the bars so they're only 5 wide. See what I just did? I just changed X scale to 5. Now, each time I'm changing the window, I'm not pressing zoom 9. I'm pressing just the graph button like Raphael said. Zoom 9 is a default. You always get the exact same graph that the TI decides for you. I like to have a little bit of control over it. Notice how there are now twice as many bars, because the bars are half as wide. So there should be twice as many of them. And you can get really ridiculous with this. You can make them too wide. But at this point, it's like, yeah, okay, it's too much detail. It's too much detail. So don't worry about how many bars you'll need in making these up. By default, go zoom 9. And then if we need to refine it, we'll refine it as we go.
Can we just do zoom fit?
Zoom fit, if I knew how the damn thing worked, yes. I don't know how it works, and I'm not sure it works for data.
It does for data, and what it does is it puts it in scale. Like what it does is it puts
Who's
it
scale?
in proportional
Who
scale.
decides?
The TIA.
Right, exactly.
puts
So
it in
zoom stat,
proportional
zoom fit, whatever you want to do. Absolutely, Raphael, absolutely. Basically, the idea, I'm going to go back to a width of 10. You guys okay with that? Decent with that graph? Now, what did you notice about all these graphs, no matter how many divisions we had of the bars? Whether it was 7 bars, or 10 bars, or 20 bars. Tapa, what are you saying?
The x-axis was still.
The x-axis goes -60 to 30, so it's still 90 wide. Love that, love that. How would you describe the shape of that data? If you had to use some words that we've talked about in the past.
It's not
Bellish.
It's bellish, yeah.
It's bell-ish, isn't it?
It's not really bell.
It's not really a bell, but guess what? Real data never is a perfect bell. Any data that's a perfect bell, you're suspect of it. It's bell-ish. What you can see is, you can kind of see this, can't you?
Yeah.
You can kind of see the rise and the fall. Any data that looks too. Remember The Fugitive? Why was Harrison Ford running? Why was The Fugitive? Who's seen The Fugitive? The movie The Fugitive? Oh, that's not enough people. Bad reference. If data's too good, suspect it. And when I say too good, if it's behaving too perfectly, chances are something's up. When it looks bell-ish but noisy, I call this noisy, slightly noisy data. Now some of you are sitting there going, how the hell do I know if it's bell-ish or bell? We'll develop measures for that in this class, I promise. Starting Monday, we're going to develop measures for how skewed off of normal something is. But this has the characteristics of a bell curve. Unimodal symmetric. It starts with tails, rises up to a common middle. It's definitely bellish, and I would call this basically a bell-shaped distribution. Fair enough. Fair enough. Where's the average in that graph? Where's the average? This guy here. Let's get rid of these guys. Where's that? This is why I changed the window. Do you see?
Yeah.
Yeah.
It's right here, isn't it? Negative 15. That's the balance point. That's x bar. That's x bar at negative 15. Let's use some color. Purple. Because why not? And this is in pounds. I should put pounds down here on the. This is pounds, and this is F for frequency. What's cool about this graph is, too, you get a nice visual of Raphael's 75% from earlier. Where's the divider for 75-25? Right? Gained weight, lost weight. So you get a great visual of that. Cool. But we get more, because we also get the magnitude of the losses and gains, which is pretty rad. Okay, fantastic. That's the average. Where's that? Where's that? And this is a loaded question. It's in a lot of different places. What are you thinking? Tammy, what are you thinking right now? Go, my friend.
It's that whole center.
Very nice, friends. Remember what Tammy said? I've erased it now to clear the board. She said plus or minus earlier. What we're going to do right now is we're going to show an application of this number. Exactly, Lucas. Boom, boom. So we're going to take this 16 pounds, and we're going to plus and minus, or add and subtract it from the average. So what we're going to do is we're going to start with negative 15. Let's add 16 to it. So that's going to see, it's going to go 15, 1. It's going to go 1 pound here. Okay? And subtract 16 from that, and it should be 31, I think. Negative 31, I guess. That entire range of values right there. I'm going to label that, let's label that little a.
Average square.
Little a, just, I'm going to tie it to notes on the sideboard over here, and it won't fit right there. That little a, that range of negative 31 to 1, has a name in statistics. That entire range is called 1 standard deviation from the mean. So let me slide this side so you can see that. There. That entire range from negative 31 to 1, that's called 1 standard deviation. And I'm going to put this in parentheses because very often it's left off, but really it's from the mean, from x bar. Very often it's just called 1 standard deviation. I'd like to offer an apology to all those out in YouTube world and you all. I can't stand the fact that this number is called the standard deviation and that range of values is called 1 standard deviation. That drives me nuts. Yes, they're related, but they're also two different ideas. I really wish they called the other thing something different, like pumpernickel, or something other than standard deviation, something besides the same phrase. So realize, when we talk about the standard deviation of a data set, we're talking about what you guys said earlier, the average distance from average. When you talk about 1 standard deviation, you're talking about adding and subtracting that number from the average and getting a range of values. I know, Sheldon. But we'll come back to that. There's a reason why we do that. A very good one, I promise. I promise. Now, you don't have to stop with 1. You can go any number of standard deviations out that you want to. So we could go out 2 standard deviations. I'm going to turn my graph back on. Yes, Athena. We could also go out 2 standard deviations. With the extent of that would be, it's just going out 16 more on each side. So starting at x bar, and going on 16, and then 16 more. That would be up to 17, I guess. And then coming down 16, and then coming down 16 more, negative 47. I think we're doing math right.
Because that's deviated from your original.
We're actually starting from center each time, Raphael. We're starting from center each time. We're starting from center each time. So you're going 32 as opposed to just going 16. So you're going 2 of these bad boys. 2 of these bad boys instead of just 1. Gesundheit, Gesundheit.
Yeah.
And thank you for bringing that up because there are some symbols that actually tie this in pretty nicely. We'll come back to that in a second. So this range of negative 47 to positive 17, that's called 2 standard deviations from the mean. I just unplugged something. Oh, I didn't. I almost did. Raphael brings up a good point. There are some symbols that describe this pretty well and pretty efficiently. 1 standard deviation can also be symbolically written as x bar plus or minus s. X bar plus or minus s. Now, if you think back to your old school Math 95, Math 111, that's how you can write an interval with using a plus or minus sign. So what it means is all the weights between x bar minus s and x bar plus s. You can also write it that way. This is all just symbols. If you don't like the symbols, you can ignore them. So you're talking about all the weights between those two values. The low value, x bar minus, the high value, x bar plus. 2 standard deviations would be the exact same thing, except you're going to go x bar plus or minus 2 of those bad boys, which would be all the values x bar less 2, all the values up to x bar plus 2. And that's where your 32 came from, Raphael. Can you go to 3 standard deviations?
Yeah.
Could you go to 4?
Yeah.
You can go as far as you want. You can use as many. Anybody ever heard of 6 sigma? Something called 6 sigma. Industry used it quite a bit starting about 15 years ago. It was used as a cost-cutting / efficiency measure. And the idea of that was 6 standard deviations.
Oh, elasticity?
Perhaps.
Is that what you're talking
Perhaps. Could be, Raphael. I'm not familiar with the term.
about? Okay.
But efficiency versus / cost-cutting, 6 sigma. Somebody in the class, could you go out 10 standard deviations? Absolutely you can. You can totally go out 10. You go out as many as you can also go out fractional ones. Half a standard deviation, 1.5 standard deviations, 0.3 of a standard deviation. It's all talking about going out a certain distance from average. Now I want to go back to Shelby's comment from earlier, because it was awesome. As soon as I went out that first standard deviation to 1 standard deviation, her face said, why? Like, why do we care? Why do we care about this? And it's a great question. It's a great question. Why do we care about this? The answer is, and you can go as far as you, like I said, you can go 3 standard deviations. This one right here, this B, is probably the most used one, and we'll see why here in a second. When you have data that behaves and looks like this data, i.e. bell-shaped data, you get some cool predictive qualities. Let's take a look at those right now. I'm going to slide over here, if that's okay, temporarily. I don't know why I'm asking you guys. You guys can see everything just fine. So, I'm going to start with a big if. If you have, and it's a big if you have data that's bell-ish shaped, and you have to satisfy that if. That's why I made it a big if. This only works, on average, in general, if you have such bell-shaped data. You get some percentages for free. For example, number 1. You know what, let me color code this with the ones we did over there. We'll do it in purple. Number 1, or letter A. About, I'm going to put about in quotes because this is definitely an ish. About 68%, or roughly 2/3 of your data will fall within 1 standard deviation of the mean, also known as x bar plus or minus s. Now, as to why it's 68%, give me some time to build that up in this class if it's okay with you guys. There's a reason why it's 68. It's a bit algebra-y and geometry-y and a little bit calculus-y. So give me some time to kind of knock those down one by one through the class, and we'll revisit why the 68 is there. But basically, what it's telling you is, when you go out 1 standard deviation and you're looking at this graph, if I was to throw up lines here and here, and figure out how much data is in that much of the bar right there, it's telling me roughly 2/3 of it. So you've got roughly 1/3 here and here, or 1/6 on either side. Now, with just the histogram, it's kind of hard to measure that. So what I'd like you guys to do is I'd like you to take a look at this data and figure out how much is actually true. How much of that is true? So in other words, how much of our data is within that range from -31 to 1? Actually, instead of using this, you might want to use your TIs now that I think about it. Since you got your data sorted already, right? Since we did that awesome sorting earlier. Let's go count. Let's go count. So let's see, -31. And students always ask me, rightfully so, very, very good question, should I count that -31 in, or is it just outside? I always tell them the same thing, do whatever you want. If it's close. 33 is definitely out. 27 is definitely in. As far as that -31, you want to include it or not include it? Your guys' call. Include it? Love it. Include it is. 1, 2, 3, 4, 5. See how I'm counting all these, friends? These are all in that interval, right? 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And that one's out, isn't it?
Yep.
So I counted 24 being in the interval from -31 to 1. Cool? So 24 we're in. What percentage is that?
24 out of 35.
It's 24 out of 35.
Isn't that the same?
Say that again. Say that again.
No, I was
Cassie?
it's close to what everyone lost at the beginning.
Oh, good, 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 good. It was close to the number of, very good. Cassie's tying that into the number of people that lost weight overall. So that's coincidental, unfortunately. Not unfortunately, it's just coincidental. So the idea is, when we look at the graph of this, Cassie, thank you for that, by the way. You look at the graph of this, roughly the same percentage are down here as are in here. So in other words, these guys over here, Cassie, make up this little sliver of this bar right here.
Okay.
Ish. I mean, statistically speaking and geometrically speaking. Very good catch, very good catch. All right? Ish. 2/3. Ish. Ish 2/3. Fair enough? That's what that says is it doesn't matter what kind of data you have. If it's shaped like that, that's going to happen ish. That's freaking cool.
Yeah, it is.
Because now you can say, how much weight did you lose? Well, it's 15 pounds was the norm. But you can be 60, 70% likely to lose as much as 30 or maybe even gain up to 1. That gives somebody a little bit more than just averaging 15. You're getting more descriptive. Is that fair? Now, a bunch of you are smiling because you never actually hear this.
Right.
Nobody actually says these kinds of things. They say, you lose 15 pounds on average. Okay, but when the data is spread out like it is in this graph, how much should you rely on just that average? I think the more descriptive you can be, the better, huh?
It's like why it's so shocking that if you ask your tired dude what the margin of error
It's only shocking because nobody talks about
nobody
it.
talks about it.
Stick your head in the oven and your feet in the freezer, and on average you feel fine. Right?
Right.
Average depth of that stream is 2 inches. Go ahead and walk across. I wouldn't do that. A few more measures, right? Okay, so anyway, let's check the second part. How about within 2 standard deviations? So 2 standards is between -47 pounds and 17 pounds. Going back to look at that data again, edit. I guess it starts with -38, right? And that's going to be, oh, here's a cool trick too. I want to jump to the bottom of the list. There's no jump to the bottom button, of course, because this thing was made in 1984. But if you just scroll up, eventually it'll put you at the bottom. So that's kind of nice. So we have to stop at 17. That means 16's in. So really, -58 was out, and 21's out. That means 33 of the 35 are in. Let's see what that is. Hot damn. Ish, 95%. 95%. And that rule is kind of part B, if you will. Let me slide the camera back over. Let me slide the camera back over.
It usually like 2 standard deviations is they're like, you could lose up to this much more gain.
Oh,
I would not
right.
want that.
Well, see, because the average is much more appealing from a mass marketing point of view. And remember, this study was done not to sell anything. This was trying to see the difference in nutrient analysis for meal replacement versus traditional dieting plans. They're not trying to sell you anything. Very often, let's come back to that, okay, Tabitha? You bring up a very interesting point. Give me 7 minutes. I want to come back to that very point. Marketing and misusing this. But yeah, give me 7 minutes. We'll go back to maybe 6.5. About roughly 19 and 20, or better known as 95% of your data will lie within 2 standard deviations of the average. And this is also known symbolically as x bar plus or minus 2 s's. X bar plus or minus 2 s's. How much data do you think is going to lie within 3 standard deviations on average? Damn close to all of it. Yes, all of it's it's for small data sets, inevitably it's all of it. So within 3, it's basically 100%. With 3, it's basically 100%. Now, the empirical rule, this is loosely called the empirical rule. I think your textbook calls it this, which is a cool name. And I love calling it that now too, because we're doing this empirically, not analytically, not theoretically. We're counting our data and seeing what falls. So let's check your guys, all of it. Your all of it data with 3 standard deviations. Let's put the graph back up. 3 standard deviations would have to go down 16 more